did the sliding window.
Yeah, and then I was trying to do it, especially on the green and I just haven't seen that in so long. Hold on.
No, it must. Like even
It's bearable.
the exam.
And then I get 40.
I mean, dynamic programming, you can, like, if you have a good algorithm. All right, hello everyone. Hello, hello. Are you ready for some algorithms? A little update, by the way, on midterms and projects. Just you might be anxious to get your grades on both of those. Projects are almost 100% graded. I just need to make a pass to make sure everything looks good, but the TAs have finished their grading. Midterm, I've finished almost all of my grading, and the TAs are a good chunk of the way through theirs. Hopefully by Friday, we have a lot of things going on besides this, but hopefully that'll be done soon. Cool. Project 3 is going to be entirely auto-graded, so you can just submit that and you'll be able to get your grade. Cool. By the way, as I was telling other people, the midterm, the average, from what I've seen so far, the average is higher pretty substantially. I'd say about 10% higher than the previous exam, just off of my estimation here. But the distribution has higher variance. So there are more people who failed the exam, and there's more people who did very well on the exam. So take from that what you will. You'll get to know your grade soon enough. More or less, if you filled out all of the problems and you attempted all the problems, you will have likely done better on this test than the previous test. That's my guess for you, but you'll see the grades soon enough. Again, if you have questions about any of the particular questions from the exam, I can go over them. Yes? So I have said that we are going to weigh your maximum out of the 2 midterms twice as much as the lower of the 2 midterms. So you should be able to recover if you did well in the second midterm, or if you did well in the first midterm, you should be okay. Yes?
Are you going to be using that part of the board? Do you think?
Not anytime soon. If you'd like to write something on there. All right. Yeah.
Sorry, I'm not too sure.
I am for the final. As of right now, because the grades on the midterm 2 were decent, I am planning on having the final also count as 10% of your final grade, and have nothing changed from that. So that is 30% overall for exams, 10% for final, 20% split between the 2 midterms, weighed more highly towards your better one. That is the plan right now. I'll see how the final grades on midterm 2 look. If they are too skewed low, I may change this slightly, but I expect that. Okay? Any other questions on the exam or the final? The final, by the way, is on the 11th, as a reminder, so that's in 2 weeks, a little bit less than 2 weeks. We are going to have review in 1 week. 1 week from today is going to be the last class. Then we do have discussion on Friday still. Last class, we're going to do some review, and then discussion is also going to be likely going to be a practice exam, but at the very least it will be review. And I will be holding office hours also to talk about all this. And I'll probably by that point have the final written, so I can give you some very good review. Okay. Any other questions on exams or the project? How many people have started project 3, by the way? Cool. Good on you. Good on you. How's it looking so far? For those of you who did it. Good. Yeah. Easier. Okay. There you go. I do still recommend that you start it earlier rather than later, but it's a more fun, easy project. Okay. So we're still doing reductions. We're going to close out reductions today and then begin our next topic all today. So as a little recap, I just want to remind everyone, this is part of the picture that we have, the hierarchy we have. We have our easiest problems that we have displayed on here. There's, of course, a hierarchy that's beneath this. But we have polynomial time algorithms, or polynomial time problems. This is problems that can be solved in polynomial time. And we have our 2 other classes, NP, which is problems that are solvable. We can return a yes answer in non-deterministic polynomial time, whereas co-NP are problems where we can return a no answer in non-deterministic polynomial time. And as a reminder of why those two things are different, we can consider the SAT problem. As we have hopefully remembered by now, the 3-SAT is where we have clauses of 3 terms ORed together, and each clause is ANDed together. This is a 3-CNF, or conjunctive normal form, and we found that that problem is in NP because if I'm given a solution, if we refer to our definition over here, if I'm given the certificate, which is the solution to the satisfiability problem, an assignment of variables such that the overall statement is satisfied or resolves to true, then I'm able to check it in polynomial time very easily. But if we look at the reverse, if I have one of these 3 CNFs, it's very difficult for me to prove that it is not satisfiable. So you can consider the idea of what information could you give me that could prove that that CNF, that 3 CNF, is not satisfiable by any assignment. And you'll realize it's very difficult to do that. So generally, we'll have some problems over here in NP, things like SAT is over here in NP, whereas its inverse, or in this case, not SAT, that is, given a circuit, tell me if it is not satisfiable, is in co-NP. So the way that you could read this is that not SAT is in co-NP means that given some certificate, I can prove that it is not satisfiable. So it's a reverse problem. It could have the same exact certificate. It would just be a satisfying assignment to the circuit, and then I could say, oh, then it is not satisfiable. It's a little bit tricky, but every problem that appears in NP has its inverse over here in co-NP and vice versa. Some problems, it's more natural to say that to phrase them as the co-NP version, to say it's easier to say that there's a no answer than it is to say that there's a yes answer. But generally, we're just going to be talking about NP, and co-NP is just this conceptual class that we'll mention occasionally, but is not going to be covered tremendously in class. Okay? Any questions on the overview? Okay? Then we have these 2 special classes, NP complete and co-NP complete. We'll just focus on NP complete again today. NP complete is going to be all of the hardest problems in NP. Basically, each of these classes, P and all the rest of them, have this same idea. So there is, in fact, a P-complete set, which is all of the hardest problems in P. And the way that we define a problem as being the hardest is we say that every single problem in that class, that is all problems in NP, can be reduced to some problem. So if all problems in B can be reduced to A, then I can say that A is NP hard. That is, it is harder or as hard as every problem in the class NP. And then if it is hard in that class, that is harder or equally as hard as every problem in some class NP, and it is in that class itself, then we say that it is NP complete. Okay, so if a problem is both NP hard, that is every problem in NP reduces to it, and it is in NP itself, then it is NP complete. And these NP complete problems turn out to be a set of very important problems, actually. We'll see another example today, another NP complete problem, but these problems end up being very interesting. They have real-world applications, and they're difficult to solve. So they are very interesting. And conceptually and theoretically, they're also interesting because if I were to be able to show that one of these problems, any of the NP complete problems that we've talked about, or any that exist, if I'm able to show that that is completable or solvable in polynomial time, then I've shown that P equals NP and I win $1 million. And it resolves a whole bunch of theoretical claims in a whole bunch of different theorems. So it's an interesting set of problems for a variety of reasons. Okay? Cool. So we first found our first canonical NP complete problem, which is circuit SAT. Circuit SAT was a problem of given some logical circuit using ands, ors, and nots, we have to determine if there exists some satisfying assignment to it. Is there some way I can assign my variables to true and false such that the overall circuit resolves to true? We've seen this a lot. It bears repeating in case anyone missed it. Then we were able to show a reduction. So we showed that this problem, every single problem in NP was able to reduce to this problem. That is, for all problems in NP, we showed a reduction from each of those problems to circuit SAT. Then we also showed that circuit SAT was in NP, meaning that this problem is in fact NP complete. I'll just use NPC here, NP-C to mean that's NP complete. Then because we were able to prove this, and we didn't do the proof in class, but you can find the proof online if you'd like. It's a bit more involved, so we're skipping it. We were then able to show our next canonical NP complete problem, which is 3-SAT. Basically, we show that for any possible circuit with ands, ors, and nots, we can convert it into the 3CNF form that we talked about earlier today in polynomial time, and then we can show that any instance of this problem I can convert into an instance of this problem in polynomial time, which is the conditions for our reduction, which I didn't write here. But the reduction is converting any given instance from this problem into an instance of this problem in polynomial time, and having the truth value, like whether it's true or false, remain the same. Okay? And then we came up with a whole chain of reductions, so 3-SAT to independent set to vertex cover, and then we also showed 3-SAT to ham cycles / ham paths. We sort of talked about both of them. The reductions are basically identical. Okay? So, just a small recap also of what is required in a proof like this. So when I want to show a reduction, I need to show, so if I want to show that some problem, say problem A, or let's say problem, let's say vertex cover. Say vertex cover is in NP complete. What do I need to show? What do I need to show? Yes. Give me one of them. It's in NP. Okay? So 1, I need to show that vertex cover is in NP. For vertex cover, just again as a reminder, this is given a graph, find a subset of nodes with size k, that is a subset of size k, such that every edge is connected to one of those nodes. So we want to cover all the edges with some subset of vertices. So 1, I have to show this in NP, which is relatively easy for this one. I just give you the solution. Show me some subset of vertices, and I can check that every edge is covered in polynomial time. Easy enough. What else do I need to show? So I need to have some sort of function. I guess I'll write the definition over here again. If I say that some problem reduces to, in polynomial time, some other problem, this means that I want there to exist some function which is polynomial time to run, such that for every possible instance of the first problem, so there's every possible instance, I have that the problem A has the same truth value on that instance as the problem B given my transformed input. Okay? So I need to have some function f that is polynomial time. So I will say that I have to design some function that converts instances of some other problem, some NP-complete problem, into this. So I need some NP-complete problem. I'll do the exact one that we did, which is independent set. So firstly, I need to do as an NP, then I need to show that some NP-complete problem or NP-hard problem reduces to vertex cover. Okay, and this has sort of 3 sub-requirements. I'll just use that as sort of the header here, right? And for this, what do I need to show? Yeah.
That the function is
Exactly. So that there is the function that I choose for this reduction is in P. What else do I need to show? I'll wait for some other hands. Sure. Yeah, so we'll do each one of them as a separate bullet point here, but we need to show exactly that same statement down there, which is here, in this case, I need to have that my independent set, I'll just use IS, of any given input needs to imply, like if this is true, then VC of FA also needs to be true. Okay? And vice versa. So because we have a 2C, because we have a two-way implication other than if and only if over in our definition, we need to have the reverse also, which is if vertex cover on my transformed input is true, then independent set on the original is also true. Okay? That makes sense? So these are the things, if I wanted to prove NP completeness, I need to prove these things. Okay? Okay. Cool. So now, let's attempt a new problem. Okay? And we're gonna use all of this again. Okay. Any questions on this before we continue? We've seen it a few times, so hopefully it's good now. Okay. So, let's introduce a new problem. Okay? And our goal is going to be to show that it is NP complete. So, the problem that we're going to talk about today is the traveling salesman problem. Traveling salesman problem, often also called TSP. So we want to show that this is NP complete. Okay? Does anyone know this problem? Yeah.
So you have and we want to figure out the shortest.
Yeah. So the problem, it may start to sound a little bit familiar. You might start to think about what reduction you want to do. Is we're going to have some number of cities. Let's say this is city A, Anaheim maybe. Okay. And we have a bunch of other cities. Let's say Boston. I'll put over here. Maybe Chicago. Whatever we want. Detroit. Sure. Whatever. A bunch of different cities. And we're going to have some distance from each city to every other city. That is, there is going to be some path. We can make them bidirectional. It does not make the problem easier, so let's just do it like that. So if some bidirectional distance between all of them. Okay, so it's going to be a fully connected graph like this, and each of them is going to have some sort of distance. You can imagine if this is like 2 miles, I guess, 1, 3, 1, 2, and 4, let's say. Something like this. So the generic traveling salesman problem, I have a fully connected graph like this, and I'd like to find some path, a simple path, or a simple cycle, I suppose, because it's going to end back at its starting point, that travels through each vertex exactly one time and has the shortest overall path. And to make this into a decision problem, remember, we are only going to be, with NP completeness, going to be talking about decision problems, problem that output either true or false. So we're going to say, does there exist a cycle, a simple cycle, with length exactly k? Or less than equal to k is also a valid way to do this. So we're going to be given some graph like this, and we're also going to be given some goal, let's say k. And I want to know, does there exist a simple path, that has a distance exactly, the distance of the path is exactly k, let's say. And no vertex is visited twice. This is a simple path. Okay? So, this is a problem. You can maybe start to see why this is a difficult problem, because it might originally seem like all the other graph problems that we've done. You know, we found MSTs before. That seems somewhat similar to this. How come an MST isn't a valid solution to this? Yeah. Exactly. So there's a few things that are wrong with it. So you can imagine an MST might look like this. We might have an MST that looks something like this. This is not necessarily going to give us a, we're not going to be able to find a cycle from this, right? So I might need to change something to be able to get a cycle, and there's no guarantees that this is going to be minimum. Yeah.
Wait, so is a simple path just the same as a hand path?
Yeah, so a ham path is just a path that exists, but a simple path has the same requirement. It visits each node one time. Yeah.
Oh, but it could repeat once.
So we're not going to repeat them in this. Okay. We are going to be allowed to repeat them if we so choose to, but we're not going to. We'll get
But
there.
like hypothetically, you could have like what if the distance from A to C?
So this is so there's a different version of the traveling salesman problem, which we will talk about actually briefly after this.
Yeah, sorry.
Yeah. So we'll answer that question. But for now, let's just look at this problem, and I want you all to consider how I might go about doing this proof, proving that this is NP complete. Remember our points here. We need to first prove that it's in NP. Then we need to find some reduction. We need to choose one of our, these are all of our known NP complete problems so far. I promise we can do it with at least one of them. And then we need to do our reduction. That is, prove that our transformation is in polynomial time and prove that after our transformation from one problem to the other, we will keep our truth value. If it's true in whatever problem we have here, it'll be true here. If it's false there, it'll be false here. Okay. So I want everyone to think about this for a second, and then I just want you to pick which problem we're going to be reducing from. So everyone pick one of those 5 problems to be what we will reduce from. Okay? And also consider the idea of why this is NP, why this is an NP. Okay. So first off, why is this an NP? Anyone want to give an argument? Yeah. Exactly. So if I give a solution to this problem, then I can check that it does in fact equal or is less than equal to k. Both are equivalent problems. And I can also check that it visits every node, and that is perfectly fine. So I can do that check in polynomial time. Relatively easy. Hopefully the proving things are in NP feels pretty intuitive. I know it might feel like a weird way to prove non-deterministic polynomial time, but as long as that definition works for you, you can just do that. Okay, and then what are we going to be reducing from? So we need to choose one of these to be reducing from to this problem. So let's just do a little hand raising, I guess. So raise your hand when I point to the one that you think we should do the reduction from. Circuit sat. People don't like circuit sat. Okay, 3 sat. Okay. By the way, all of them are in fact possible, so it's not that there is going to be an objectively correct answer. There are going to be some that are going to be easier to do, easier to formulate. This is a little bit of a personal choice also between what problems you enjoy more. Independent set. Vertex cover. Ham cycle. Okay, cool. So ham cycle is the most naturally connected. They both have very similar properties. In ham cycle, we're trying to find some path that goes through every node. We want to know if one exists. And in traveling salesman, we just want to know, is there one that is exactly some length? So it seems like this is a more constrained version of that problem in some ways. Or I guess maybe a less constrained one, we'll see. So it's a very natural choice here, okay? Let's consider for a moment how we could do this reduction. Anyone have any ideas originally? Now let me ask this question first, I suppose. So if we want to now do the reduction. We're trying to prove that ham cycle. So we're trying to prove ham cycle is going to reduce to traveling salesman in polynomial time. What am I going to need to do? What does my function f need to do? Open problem. Someone tell me. Yeah. Okay. So you're saying that every traveling salesman problem can be written as a ham cycle problem, or can be converted. This is backwards. Like I said, this is one you really have to be careful of. People will do this backwards. The reduction, one way that I think is easy to remember it is the reduction is read left to right. I am reducing a ham cycle problem to a traveling salesman problem. So I'm reducing ham to TSP. And you can also imagine, you can visualize what is happening like with the set of problems. So if I had all of my ham cycle problems, right? All my ham cycle problems, and I have all my TSP problems, just drawing them as blobs. then what you've said is I want to show that every one of my traveling salesman problems can be written as a Ham cycle problem, right? So all of them can, some subset of the Ham cycle problems, I can do this. That means I could use a Ham cycle solver to solve every one of these problems. Now the problem with this is that it doesn't say anything about the difficulty of these problems, right? So it could be that Ham cycle is harder than TSP, and in fact this would be showing that, which isn't what we're trying to show. We're trying to show the reverse. So in fact it is the other way around. We want to show that the set of all Ham cycle problems reduces to some subset of TSP. Yeah, so this is the reverse of what we wanted to do. Yeah, Amanda. Basically, we want to show that we have some function that can convert all of the Ham cycle problems into a TSP problem in polynomial time, and then we could solve it with a TSP solver, meaning that the truth value remains the same. Okay? Yeah, so in fact, we are doing it this way. Our function f is converting that way. Okay. So we want to find some function such that given any Ham cycle problem, you can imagine that is just any graph. We're given any graph, we'd like to find out if it has a Ham cycle, and we want to find some way to convert that to a traveling salesman problem such that if the traveling salesman problem is true, then the Ham cycle did exist, and if it's false, the Ham cycle did not exist. You all understand this? Okay. Okay. So I want you to spend just a minute to think about this. See if you can come up with an idea here. You can talk to your neighbors if you so choose, but just take a moment to ponder.
So we also want cycles for traveling salesman.
So yeah. Also cycle. You can have not a cycle if you so choose. That's a similar problem. Yeah. There are a lot of variants of TSP.
Yes. That's what happens.
I just don't understand why. Also remember that
Okay, so just to show you what we're doing, what the transformation we need to do, what f is doing is it needs to take some graph that we want to check if it has a Ham cycle, that is a cycle that visits every node exactly once, and we want to convert this somehow into an instance of the traveling salesman problem, which is also a graph, but it's a graph and it's an objective k, which is the length of the cycle. So we've added weights so that this new g after we go through f, we need a new graph which has now weights on the edges and also has some goal k, which is the length of the simple cycle that we want to find. So it's perfectly possible that I could have a graph that has a Ham cycle in it. If I were to just take it, I could still fail the traveling salesman problem because the cycle is too long. Its weights are too high for our goal K. Or too low in our case, but we'll say too high. Yeah. So we'll allow for this one, we'll allow bidirectional in our Ham cycle. They are equivalent problems, Ham cycles with bidirectional or with directional. Let's say with bidirectional, just to make this a little bit easier. I can just promise you that they are the same difficulty. You can do the reduction between them. Yeah. Yes?
Sorry, did you say earlier that?
Yeah, so we're not really using the TSP solver, but we're showing that the truth value remains the same. If we wanted to use this in practice, then we would use a TSP solver, if we have a really fast TSP solver. I think you were first in the back. Sorry, you. You're just behind someone, yeah. Yeah, yeah.
You're just saying in the
I'll call it G prime. So this could be a new graph. It doesn't need to be the same graph, but it is a graph still. Yeah.
like an added parameter of K.
With an added parameter K and also all of the weights on all the edges. Yeah. Yes.
And so
Yes, we decide how to assign the weights. We are creating G prime. We're saying, given G, how do we construct G prime and K such that the truth value is the same?
oh, we also construct K as
Exactly, exactly. Yeah. So we just get given an instance of Ham cycle, and then we create from that, we create some function that takes one of those and turns it into a traveling salesman problem. So it can be a totally different graph if we wanted it to be. It can be whatever choice of K we'd like to. Okay? Yes.
We can arbitrarily decide
Yes, yes we can.
find the Ham cycle.
So we can't find the Ham cycle. So we can't find a Ham cycle because finding a Ham cycle takes greater than polynomial time, perhaps, or at least we don't know it takes polynomial time. Yeah.
Can I give like a tried solution?
Yeah. Yeah. Absolutely.
Can we just like say finds just a valid ham cycle?
So let's look at this real quick. So if we were to just take our, let's say we have some graph, and we're going to allow bidirectional edges. Like I said, that's an equally hard problem, so it's perfectly fine to do. We say that we have some, let's say there exists one, right? I'll say that I also have this, let's say. And what you're suggesting is that we convert this into being the exact same graph, right? That is all of these same exact edges, except all of them have weight 0. 0, 0, 0, 0, this one, and 0. Okay? And then you said k is equal to 1.
Assuming like the less than or equal to.
So if we allow less than equal to, then sure. We can also just say it's 0. That's fine. Because we know that if I find 1, it'll be 0. So this is a reasonably good starting point. This is basically the transformation we're going to do. The only difference is I did actually say that the traveling salesman problem has to be fully connected. So that's the one thing that that you didn't capture with this. Any ideas immediately how to deal with that? So I add edges between everything that isn't connected, and what do I weigh them? Sure, I can also just give them 1. So I give all the other ones 1, then this would in fact be a valid transformation. Yeah, Amanda. Means you can go either way on them. Yeah.
Are we using Ham cycle?
Ham cycle. Yeah. Cool. Anyone else?
Isn't that graph impossible?
No.
Not the first
one. Okay, any other questions? Okay. So now I'm going to give you a slightly different problem. So this will work. We have to do the proof both ways, but it is a pretty intuitive proof. I think basically everyone has probably clicked already why this is true. If there doesn't exist a simple path with weight 0, then there did not exist a simple path here, or a simple cycle here, a Ham cycle here. So we can pretty easily prove this both directions. If people would like, I can cover that, but I think it's relatively straightforward. Yeah.
Explain why you added that.
Because the traveling salesman problem is defined where it has to be fully connected. Ham cycle isn't. Ham cycle can be an arbitrary graph. The traveling salesman problem needs to be a fully connected graph.
So you added
So it's not what I'm going to take. There's no algorithm running. It's that the truth value of this will be true only if this is true. You can see because I chose k equals 0, that is my cycle has to have a total weight of 0. It is impossible for one that is doing that to take that path, as long as I have no negative weights on my edges, which I don't. Yeah.
But fully connected means
Yes, exactly. Every node is connected to every other node. Any other questions on this? Okay, so we can, yeah, Amanda?
why is this like Azure 1?
Because we need to make it fully connected. If I made this a 0, then I've added new options that I didn't have in the original graph, and it might be that this has a traveling salesman solution, or this didn't have a ham cycle solution. So if I made this 0, then I'm allowed to take it, basically to get a traveling salesman solution. But if I make it 1, I'm not allowed to, because my maximum weight along my cycle is 0. You understand? Okay. Any other question on this? You have a question? All right. So this is one variant of TSP. This is the generic traveling salesman problem. This is the most broad one that you'd find. But it's not necessarily the most useful, and there are in fact a lot of different variants of the traveling salesman problem, and we'll talk about one that's slightly more useful right now. But for now, I'm going to assume that the proof of showing that that the truth values of these are equal, I'm going to assume that you all can handle that. It's relatively straightforward. You just need to show if this is true, then I can take the exact same path here. Traveling salesman is true. If this is not true, then it is impossible for there to exist some cycle that has length 0 here because there is no ham cycle. Therefore, these two share the same truth value. Okay. If you'd like to sit down and prove that more formally, you're welcome to do that on your own or come to office hours. I'll explain it more thoroughly. But that is the gist of the proof. So this is now added to our graph here, TSP. Okay? But this is not a tremendous, this is a useful problem, but there are many other situations where this could be a lot more useful if I restrict this just a little bit more. So what we're going to do is we're going to look at a variant of this problem that is a lot more useful in practice. This problem is the metric traveling salesman problem. MTSP, if you'd like. And the metric traveling salesman problem has the following restriction. My nodes need to obey geometric space. So you can imagine I have geometric space, these nodes are placed on them. That is, in particular, if I have some triangle of nodes like this with distances, it must be the case that C is less than or equal to A plus B. Anyone know the name of this? Yeah?
triangle is equal.
This is the triangle inequality. It's a very famous inequality, very useful in a lot of mathematics, surprisingly, but does come up a lot. This is the triangle inequality, and the metric TSP adds this other constraint, which is for every triangle of nodes, essentially, this must be true. An alternative to this, a way to think about what the metric TSP problem is that it must obey geometric space. That is, it must actually be, like you can imagine I have like a sheet, and I've placed my nodes on them, and I need to visit them. You can see that this is immediately a more like realistic type of problem for something like a traveling salesman. The things can't have arbitrary distances from each other. They need to be related geometrically. Obviously, there can be variants of this. This problem is actually extremely useful, and we actually see a situation where we do need to solve this problem in the real world when it comes to making PCBs. So you can imagine when I'm making a PCB, that's a little circuit board, in case anyone doesn't know. there are a whole bunch of positions I might need to put transistors, I might need to put whatever on here, and I need to navigate through all of them and either drill a hole or solder or whatever I need to do, and I need to visit every single one of them, and I need to do it as fast as possible. This is exactly a metric traveling salesman problem. So there can be tens of thousands, if not millions, of these locations that I have to visit, and so we actually care about a relatively large N also. So this problem becomes, as I was saying with the other NP-complete problems, becomes a very useful problem, and one that having a very efficient algorithm to solve is very important. Okay? Hopefully that's a good justification for this. So, now, the reduction for the metric traveling salesman problem is very similar. Can anyone tell me how it's different? I'll give everyone a second to think about it. Yeah, good guess. So we can't actually do that. So if I did infinity, you can imagine if these two edges do actually exist, I have 1, 1, let's say, then I have infinity. Then sure, 1 plus 1 is less than infinity, but infinity plus 1 is not less than 1. Get it? Or it's not, no, it is greater than. 1 plus 1 is not greater than infinity, sorry. Yeah, yeah. Or greater than equal to infinity, yeah.
Okay, so to be clear, the reason why
Exactly, exactly. Yeah, so if we had the same exact situation, but if we just tried the same exact reduction, we could end up with 0, 0, 1, which doesn't work. Yeah, yeah. Close. 1.5 also wouldn't work. I'm pretty sure. Here, let's draw it up. Yeah. So if I had 1.5, 1, 1, then label this C. Label these A and B. Or no, that's fine. Yeah, you're right. No, other way around. So these two, and then that one would be this greater. Yeah, that's fine. Okay, sorry. I thought it didn't work. Okay. Maybe someone. Yeah, sure. That should work though. That should work then. Yeah. Okay. Sorry. The proof that I've seen for this always uses 2. I actually thought 2 was necessary. Let's call it 2 just to make it simpler. And just sorry in case I did something wrong. So in fact, we're going to label all the edges from the original graph 1 and all the other ones 2, and that will obey the triangle inequality on all our edges. Okay. So it's a relatively similar reduction. You can think about it offline if you'd like. This isn't going to be the point of this thing.
I was just going to say, what would
Yeah.
K be equal to that?
K would be equal to the number of vertices. So K would be equal to V. Yeah. In this reduction, we would do this, and then K would be just the size of V, because we need to visit each one time. Yeah, and you can't ever take one of the 2's because then you would require greater than V. Okay, cool. Does that make sense? Okay. So the point of talking about this problem, the reduction ends up being very similar, and we can just add it to our graph here if you'd like to. Very similarly, MTSP. Interestingly, by the way, I'm going to challenge you similarly to the ham cycle ham path one. Try to do a reduction from TSP to MTSP, and you realize it's actually non-trivial. They are extremely connected problems, but it's difficult to do that, but it's easy to use the same problem to do the 2 reductions. Same as the ham path and ham cycle. Reducing from one to the other is actually surprisingly difficult. Okay, so the reason I want to talk about this problem is our next topic. So we've done a lot of reductions. We've talked about these problems. We've now introduced a little bit why they're important. But now, how do we deal with them in the real world? So imagine I have, n equals, or the number of vertices is enormous, the number of edges is enormous for some traveling salesman problem. You can imagine even our TCB example, or PCB example. It could end up that I have a really, really hard one of these problems, and by the nature of NP-complete problems, there aren't very fast algorithms to solve them in general. There are good fast algorithms, but not polynomial time. That is, they still have this exponential behavior, and if I have a large enough size of my problem, it can get really bad. So what do I do in practice? Any guesses? Yeah. Randomize. So there are randomized algorithms to solve some of these problems, which we could try doing randomized algorithms, but randomized algorithms will not necessarily work well in practice, and they have one particular thing that happens to their output. And we can just do that directly instead for this, yeah?
Approximation.
So we can find some approximate algorithms. So the next big topic for us, this is what we're going to cover for the rest of today, and also Monday next week, is approximation algorithms. So it turns out that there's a lot of problems that are very hard for us to solve in a reasonable amount of time that we might call intractable. This problem is metric traveling, to be realistic with you, can be solved fast enough for most real-world applications, but there are problems that are not, that we need to do approximation algorithms for, and you can imagine for things like the PCB, we might still need to do that for them to be fast. So for this problem, we need to come up with some solution that is close to the right answer and is bounded in some way to the right answer. So what we're going to do is we're going to define that this problem, and also it's important for us when we're doing an approximation algorithm, we're talking about the minimization problem now, not the decision problem. I can't approximate true and false, but I can approximate what the minimum distance for my simple cycle is. So we're going to be talking now about the minimization problem, which is find the minimum distance cycle for the metric traveling salesman problem, okay? And we're going to define an approximation algorithm. We're going to say that some algorithm, let's call it algorithm, which we'll just call approx. Okay, we have our function approx, or our algorithm approx, is going to be k is going to be n, or is going to be a. I'll use a different letter for this. I'll say that it is a d approximate algorithm. If and only if for all instances of our problem, for all instances of the problem, the ratio between the approximate solution and the optimal solution, which we'll just call opt, has to be less than or equal to d. Okay. So to break this down again, the approximation algorithm, we'll say we have some approximation algorithm, which I'll name approx, and I'll say that it is a d approximate algorithm if and only if, for every possible instance of the problem, my approximate algorithm has a ratio to the optimal that is bounded by d. Right? So the ratio between how well I do and how well the optimal does is less than or equal to d. Okay? So this is for minimization problems. Anyone want to guess what it is for maximization problems? So if instead of minimizing, so of course as as this is larger than opt, because opt is the minimum, so approximate can only be greater than that, then I'll have a large ratio. I can say that it's a 2 approximate, means that this is 2 times as large as this. How about if I'm doing a maximization? So if instead I'm trying to maximize something, then how would I write this? Yeah.
Is it just a flipped?
Exactly, I can just flip the ratio. So this is if it's a minimization problem, it's like this, and if it's a maximization problem, it is the inverse. It's just opt I over my approximation on I is going to be less than or equal to d. This is for a maximization problem. Okay? Cool. Does that make sense? Okay, so just some way for us to define this. It is difficult sometimes. The difficulty here is that we don't know opt generally. We can say things about the optimal, but we need to prove this ratio without necessarily knowing the optimal, because this is for all possible problems. The ratio is the ratio between how good our algorithm is to how good it could be optimally. How good is the optimal algorithm? Yeah. Would D be what? Sorry, what? A tolerance? So tolerance would be something else that we define for our algorithm. I could say that I have a tolerance of 10%, therefore I want an approximate algorithm that is 1.1 approximate. They are related terms, but they are different. Like, this is a theoretical definition. Tolerance is more of an engineering constraint. Yeah. Yeah. Yeah.
Is there a d-value at which
I suppose if d is an exponential function of n, then probably we don't care about it, but it still is a thing that I could say. I could still say that it is exponential, like n factorial approximate for the most part, but not a useful thing to say generally. Yeah. Usually what we care about in practice are either constant approximates or sublinear approximates is usually things that we might care about. Linear and above we usually don't care about at all, because that means that our problem gets arbitrarily bad. Yeah. Okay. Any other questions on this definition? Yes. If my approximation always overestimates, yeah, I mean you can get a relatively low d. Yeah. The objective generally for us as algorithm designers is to find the lowest d possible. So if you had a d of 1.1, great. It depends on your problem, but you've had a relatively low d. But if it is 100, perhaps in practice that's terrible for me. Yeah. No, because that would increase d. So if I'm looking at a minimization problem and I increase approximate, then d, like this ratio goes up.
But like for a maximization problem.
For a maximization problem, well, I still need to find the solution that A is returning, and we can maybe talk about some maximization problems in the future, but we're going to look at a minimization problem today, and you'll see that returning the lowest thing doesn't make sense. I still need to return a valid answer. For example, in the traveling salesman problem, I still need to return a path that visits all my nodes. So I can't just return 0. I need to return a valid one of those, and that's why I can't just say approx equals 0. Yeah, make sense?
So we're not looking at decision problems anymore.
Now we're looking at optimization problems. So this decision problems basically exist just in this complexity class. It makes it easier for us to say things like a problem reduces to another problem, but generally there's an equivalently difficult problem with it, which is an optimization problem. So for metric traveling salesman problem, for example, finding the minimum traveling salesman path, the one with the minimum cost, is an equivalently difficult problem as finding one with an exact distance. Yeah. Okay? Does that make sense? Yeah. So we're just now reframing them as optimization problems so that we can talk about approximation and talk about the actual use cases of algorithms like this. Okay. So let me check the time real quick. Okay, we don't have a ton of time. I think I'm actually going to leave the metric traveling salesman problem as an open problem for you guys to think about, the approximation, but I'll do a slightly easier one in class so we can talk about a different approximation algorithm very briefly. So this one, I'll give you a hint by the way. Start by considering an MST, okay? And see how low you can get with this. We'll talk about it on Friday perhaps. Maybe I'll even throw this into the discussion so you can work on it. But it's not too difficult, but I just want to do a different one because it's a little bit more straightforward. Okay. Any questions on this before I erase? Yeah?
I was just wondering.
Exactly. We'll see that in a second. We'll see an example of how we can get some D without knowing the optimal. So let's look at a slightly easier problem first. So let's look at another problem that we're very familiar with, vertex cover. So let's talk about vertex cover. Sorry, I took a little bit longer with the other stuff than I thought, so I'm going to just skip to vertex cover. So vertex cover, as we all remember, is given some graph. I want to find a subset of nodes that cover all of the edges. Now our optimization problem for this is going to be find the minimum sized subset. So find the minimum size subset that covers all of our edges. Okay? So it's going to be a minimization problem. This is our definition of approximate. I'm going to have to erase this right now, so if you want to take a picture of something, do it right now. Everyone, okay, sure, go for it. And I want you all to consider how we could approximate vertex cover. So is there anything we could do? In particular, I'm going to tell you all that we're going to aim for a 2 approximation for vertex cover. So take a minute and think about this and see if you can come up with an algorithm. I'll give you like 3 minutes or something. So I've written out the definition here again. So vertex cover, we are given some graph, and we have to find some subset S of the vertices such that every edge has one endpoint in S, at least one endpoint in S, and we want to minimize the size of S. That's our objective. And now we want to write an algorithm to solve this that is polynomial time that gives us a 2 approximation. 2 approximation, remember, means that this minimization, we are within 2 of it. The size of our subset is within 2 of the minimum possible subset with this property. Yes? As in by a factor of 2. By using exactly our definition from before, so that is the subset of ours for any instance, the size of our subset is within a factor of 2 to the optimal subset for all instances of the problem. Okay? That makes sense? So for every instance of the problem, vertex cover, our algorithm will return something which is within a factor of 2. And we're returning the size of our subset. Okay? Okay. Give it another moment. See if you can come up with an algorithm for this. For traveling salesman, not for this one. Okay. So this is the first idea: is choose nodes in order of highest degree to lowest degree. Do people think this is going to work? So we can imagine some graph. So it's intuitive. You can imagine if I have like a graph like this. I have all of these nodes here. It makes sense if I just choose the one with the highest degree, and I repeatedly do that, it's very likely that I would, in this example, I cover them immediately. But is this necessarily going to give a 2 approximation? And how could we show that also? So I'll leave this as a little question mark. I'm going to say this is not the intended solution. So you can continue thinking about it. Think of a different solution perhaps. Yeah, do you have one? So walk through all of the edges and then pick the one with the highest degree it's connected to and continue. This is a very similar problem to this. In fact, you are just going to be biasing towards choosing. So this is you basically have found like a randomized version of this same strategy. It depends how you walk through your edges. If I randomly pick an edge and then I choose the one that's higher out of them, continue, you just have a randomized version of this that has the same problems. That make sense? Yeah. Yeah, so I assume that was the statement here is once now that you choose these, anyone that has no edges that are still left. So like if I had another edge here, then I could still choose this one, but I wouldn't choose any ones that don't. This is a good intuitive idea, but I'll give a different answer for this one, and you'll see that the answer I'm going to give is going to be very easy to prove is too approximate, and this one I believe is not too approximate actually. You can try that on your own if you'd like. Yeah. It's within a factor of 2, so it's not like plus or minus 2. It's a ratio of 2. It's at most twice as large as the optimal, as the minimum possible subset. Okay. And we have enough time. I want you guys to truly attempt this problem. This is going to be the basis of a lot of what we're going to do in the last 2 days here. So give it a try. This will appear on the exam as an extra motivation, I suppose. Okay. So I'd like to hear some ideas. Utkarsh, I think you'd go first. Any ideas? Same idea as him. All right, fine. Yeah. It is not immediately obvious to me how you would turn this into a vertex cover. So, for example, it is totally possible that I have to choose neighboring nodes. For example, if I had something like this, where I had 2 nodes like this, then the minimum cover is 2, is picking both of these. And all the rest of them I wouldn't cover. So I'm not sure exactly how, for a situation like this, your algorithm would work. It is a good idea to try to think about other algorithms you know. That's a good built-up intuition, but I don't think that would work for this problem. Anyone else? Any ideas? Okay. Okay. Well, let's think about one thing, okay? Let's think about, so 2 approximate. 2 approximate. 2's fairly big number when it comes to these subsets. We can imagine what an optimal looks like, and we can think about what we're allowed to do with that optimal, right? So if I have some subset, you can imagine that I have like each of these and maybe like this, something like this, right? If we have our maximum subset, which is just going to be this one and let's say this one, then if I have a 2 approximate, I'm allowed 4 nodes, right? So you can imagine there are going to be situations where I'm allowed to choose both along some edge, right? So both here and let's say here, I could choose that, right? So in some way, you can imagine that for every essential node, I'm allowed to have an extra endpoint for one of its edges. I guess consider that thought for a little bit and see if maybe that can inspire you towards the answer here. I will give an extra little bit of hint, which is the intended solution here. We do, in fact, choose edges and then make our decision from a subset off of that somehow. So we repeatedly choose edges. You can think about that. That's whatever. Yeah.
What if like every time you pick a node with the highest order of edges, you take
I don't think that would be more helpful than choosing the second highest order, but I like where your head's at. Yeah. Okay, so I'm gonna I think unless anyone has any ideas, I'm gonna just talk about the strategy here. The strategy is relatively simple to state, but the difficulty is in proving it's an approximation and also looking at why it is not lower than 2. So here is the strategy that is sort of the canonical 2 approximation for this problem. If I'm given some graph, let's just draw an arbitrary graph. Give me 1 second to draw it. Something like this, maybe here, here, and here. Something like this. So what we can do is we can choose a random edge. So we can just sort them arbitrarily, and then choose one edge. Let's say this one here. And then we're going to add both of its endpoints to the subset. So what I was getting at previously is for every edge, at least one of its endpoints is in the subset. We're going to add both of them. Then for all of the edges that are coming off of the nodes that I've chosen, I remove them as possibilities. I'm now no longer able to choose those in my procedure. Then I randomly choose another node, or another edge, let's say this one. Select both of these, all their neighbors get deleted, I can no longer choose those. And finally, I choose the last remaining edge, this one, and I mark both of these as part of my subset. So you'll notice that the actual minimum here is that, and that is 3, and we have now marked 6 of them. Okay? So what we find is that every single graph you can possibly construct, this strategy will return a number of nodes which is less than or equal to 2 times as many as the optimal. Okay? Any questions on this algorithm before I continue? So again, the algorithm is that I arbitrarily choose an edge, I add both of the endpoints to my subset, and I remove all edges that now would be already covered by my subset. And then I repeatedly do this. Make sense? I still see a little bit of confusion, so I'm hoping to maybe get a question. Anyone? Okay. Yeah.
Maybe this is getting ahead to the set of like nodes that we mark.
Yeah, it will. It will, yeah. So it isn't part of the proof, but it's interesting. I think.
Because if that's true, then you
I
can
do
use
think
this
we
to
know.
try to make a better thing to actually solve vertex cover.
Yeah, no, I don't think it is. I actually don't think it is true. I'll consider this. I haven't considered that before, so I'm not gonna answer it online. Yeah, no, I'm good. Yeah.
Can you take this?
Possibly, but there is no guarantee that we. I mean, you could perhaps come up with a procedure, but I have not stated any procedure where we can trim down on all of these. If you find one, that's good on you. I think that the actual approximation we can get on this upon end of time is quite a bit lower, but you can try to improve on this algorithm if you'd like. This is just a relatively easy one to state. The question, though, remains to us. The thing that we still need to prove is this. Is that by doing this procedure, so our algorithm will return this subset. How do we know that that subset, one, will be a valid vertex cover, and two, has this bound on the approximation ratio? So firstly, how do we know that it is in fact a valid vertex cover? Yeah?
We don't stop.
Exactly. So we mark each of the edges either by explicitly saying, like choosing the edge, which obviously will make it marked, and all the rest of them we only remove if they're marked. And we go through all of the edges that are not marked. So we will have basically a while loop that is while it's not vertex covered, continue. And eventually that will end, and that will give us our subset. The slightly more difficult question then is, why is this a 2 approximation? How do we know this is a 2 approximation? Yeah.
For every
Exactly. So we can consider the number of edges that we've chosen. So I'll say that the number of edges that we've chosen, we know that each one of them is disjoint in the way that they aren't covered by the same vertices at all by their definition. So we know that optimal is at least that number for any art. The number of edges that we chose is a lower bound on optimal. Okay. Secondly, we know that our algorithm chose exactly 2 times that number of them. Does that make sense? So because there's going to be 2 times the number of edges we chose, I'll use E to represent edges, just make it maybe more clear. So our algorithm is exactly 2 times those number of edges, because that is how our procedure works. But we know that for every one of these edges, in optimal, at least one of the endpoints has to be chosen. That's exactly what you said. So by combining these 2 things, we can see that in fact we get that algorithm is going to be. I'll rewrite it as this: 2 times the algorithm is going to be a lower bound on opt. It's going to be an upper. An opt. Sorry, other way around. Sorry. Yeah, other way around of opt. So optimal is at most 2 times larger. This is just a rephrasing of this same objective. If I just combine these 2 terms, I know that number of edges is equal to alg over 2. I can replace them and get this. Okay. Does proof make sense? Yeah.
So can you just give the intuition?
Yeah. So this is the most important part of it, sort of, is that for every one of these edges we chose, we know that none of them share any endpoints by the way that we've constructed all of this. So every one of them has to be covered by at least 1 vertex, right? That is the number of vertices needed for a cover of this graph has to be at least the number of edges that I chose this way. Make sense? Because they can't both be covered by the same node because of my construction, because I've deleted all things that would be chosen that way. So at the very least, each one of these needs to be covered by 1 node. Cool? Make sense?
Wait, but isn't that at most?
So optimal has to be
Oh,
greater
never
than or
mind,
equal to
never
number of
mind,
edges.
never
Yeah. Because it could be that the opt has to be larger, but it is at least this many. Yeah.
I'm sorry, but I think the last
This one? So alg is, so we're gonna have a is less than or equal to 2 ops.